Welcome to the third part of Unit 2. In this part, we're going to look at two new quantities. One's a vector velocity, the other one's a scalar speed. To begin with, let's start with the one you're most familiar with, which is speed. Speed is the distance an object travels in a time interval. So in symbolic notation, we'd say speed, which is s, equals distance, which is d, divided by a time t. So speed is distance divided by time. In your car, you have two ways of determining your speed. The one way is you can look down at your speedometer. The other way you could do it is by using your odometer. That's the one that tells you a distance, and a clock. Okay? These two measurements give you slightly different values, maybe not even slightly different values. Okay? What your speedometer is telling you is it's telling you your instantaneous speed. Instantaneous. I can spell instantaneous speed. It's telling you how fast your car is moving right this instant. Your odometer and your clock are going to give you your average speed. Okay. How fast did you go on average? So let's say on a trip, your average speed is 50 kilometers per hour. Is your instantaneous speed ever more than 50 kilometers per hour? The answer is it has to be, unless for that entire trip you were traveling at a constant speed. So now let's think about a normal trip. So you leave wherever you're starting from. You probably have some stoplights and stop signs or something like that, and then you jump on a highway or an interstate and go for a little bit, and then when you get done on the highway or the interstate, you probably have some more stop signs and stoplights, which means at some points on this trip, your instantaneous speed was 0. You were stopped at a stop sign or a stoplight potentially, which means at other points on your trip, you had to be traveling faster than 50 kilometers per hour in order to get the average over the whole thing to equal 50. Okay, so that is your speed. Okay. Velocity. Velocity is a very related quantity to speed, but subtly different. Okay, velocity is displacement in a time interval. So speed depends on distance. It's going to care how far you traveled over the whole thing. Velocity cares about displacement. Where did you start? Where did you stop? Right? And I don't care how you got from one to the other again. Okay. Velocity is displacement over a time interval. Remember displacement, as we saw in the last unit, was delta x, change in position, divided by a time interval. Sometimes you'll see this written as a t. You might also see it written as a delta x over a delta t. If you have starting and stopping times, then you need to take the change in them to get the length of the time interval. And in both of these cases, that gives you the velocity. Now, just like with speed, you can have an instantaneous velocity and you can have an average velocity. The instantaneous velocity, so instantaneous, I gotta try to spell that again, instantaneous, tells you how fast you're going and the direction that you're going. Okay? It is the case that the size of the instantaneous velocity is the instantaneous speed. I really need a smaller word here. Okay? Okay, so instantaneous velocity is your instantaneous speed with a direction tied onto it. Okay, which is often why in physics you'll ask, or you'll see speeds referred to with the letter v, because they're looking for the instantaneous, or they're talking about the instantaneous, how fast it's going at one particular instant. You can also have an average velocity. Okay, average velocity is not a question of how fast and what direction like you had for instantaneous velocity. This one really you have to go back to the definition, delta x over a time interval. Because remember, delta x, the displacement for a round trip could be 0. And because of that, your average velocity would be 0, whereas the speed for that trip would not have been. Okay. So, a couple of questions, very similar to the ones we had at the end of the last unit. Is it possible to have a non-zero average speed and a 0 average velocity for a trip? The answer here, again, is no. To have a non-zero average speed, wait, hold on. Non-zero average speed, and I've got the questions backward from last time. So change this. Is it possible to have a non-zero average speed? Well, to have a non-zero average speed, remember speed is distance divided by time. To have a non-zero average speed, I have to have gone some distance in some time. And a 0 average velocity for the trip. Well, what if that distance I traveled, again, was in a full circle? Start and stop at the same point. That means that my average velocity, delta x over delta t, or delta x over t, will be 0 because I'm starting and stopping at the same spot. So average speed is non-zero because I've gone some distance in some time. Average velocity is 0 because I'm starting and stopping in the same location. So answer here is yes. Is it possible to have a non-zero average velocity and a 0 average speed for a trip? To have a non-zero average velocity, that means my starting and stopping positions are different. And if my starting and stopping positions are different, I have to have traveled some distance. And if I have to have traveled some distance in a time interval, then I do have a non-zero speed. So the answer to the second one is no. Okay. Can your average velocity equal your instantaneous velocity? Sure. Why not? What does it take to get your average velocity to equal your instantaneous velocity? Okay, well, the first thing is you have to have a constant direction. Okay, the second thing you need is you need to be traveling at a constant speed. Okay, why do I need these two pieces? Okay, well, if I'm going in a constant direction, that means I'm not changing direction at all. So I'm traveling in a straight line. And by traveling at a constant speed, I'm keeping the rate of that travel the same. Okay. Now you're like, but somehow you had to get to there. Well, yes, I admit. But let's pretend that you're on a really, really long road. And you start your measurement here. And you stop your measurement there, and you don't care what you were doing before this position. You don't care what you were doing after that position. But for the position in between, you had the cruise control on. You're going in one direction, always the same speed. And over that particular time interval, your average speed would equal your instantaneous speed. There is one special case that really is an example of the previous one, but deserves mentioning on its own. What happens if those two spots are the same? What happens if my starting position is here and my ending position is there? In other words, I'm not moving. A instantaneous speed of 0 that stays 0 and isn't going to change from 0 for the entire duration of the calculation or the measurement would also give you an average speed or average velocity that equals your instantaneous velocity. Okay. So one last thing to think about. I have 4 cars here. One traveling in a straight line with a decreasing speed, one traveling in a straight line with a constant speed, one traveling in a circle with a constant speed, and the last traveling in a circle with an increasing speed. And my question is, which of these 4 cars has a constant velocity? Okay, so remember, velocity is a displacement divided by time, right? And it is a vector. So anything that is changing direction is not going to have a constant velocity because the velocity is changing as the direction changes. So that rules out 3 and 4. The other thing my velocity has, it has a magnitude or a size. And if the size of the velocity is changing, if the magnitude of velocity is changing, then my velocity is not constant. Okay, that eliminates number 1. Number 2, car 2 is traveling in a straight line, so my direction's not changing, with a constant speed, so my magnitude is not changing. Therefore, only car 2 is traveling with a constant velocity. Okay. The other 3 cars do not have a constant velocity, and we would say they are accelerating. And that is the subject of the last video for this unit.